Welcome to this course on linear control systems via the frequency approach. In today's lecture, we will learn about the Laplace transform and the transfer functions for linear systems. So we start by considering the following electrical circuits. So we have here an input voltage, U of t, we have a current, I of t, a resistor, and a capacitor, and the voltage of the capacitor is Y of t. And the goal is to find a relation between the input voltage U of t and the output voltage, so the capacitor voltage, Y of t. So we first apply the Kirchhoff voltage law. We obtain U of t is equal to the voltage across the resistor, R times I of t, plus the voltage across the capacitor. Okay. Then we know that the current through the capacitor is equal to the capacitance times the derivative of the voltage through the capacitor, so dy over dt. As a result, if we replace I here by this expression, we get that U of t is RC times dy over dt plus Y of t. Now, the latter equation, if we divide both sides by RC, what we get is dy over dt plus 1 over RC times Y of t is equal to 1 over RC times U of t. So now we call this a differential equation. Differential because we have a derivative here, the time derivative of Y of t. Okay? So we have this system, this circuit, the input is U of t, the output is Y of t, and the relation between these two signals is a differential equation. Now, if you take more general circuits and more complex systems, mechanical systems, hydraulic systems, thermal systems, and so on, you get a differential equation between the input and the output. And this differential equation can have more than one derivative. You can have up to the nth order derivative for the output and the mth order derivative for the input. So the general form of a linear system is as follows. So we have here on the left hand side, Y of t is the output of my system, and I have the outputs with its time derivatives up to the order n, and on the right hand side I have the input and its time derivatives up to the order m. So you see that here it becomes quite complicated. So as the system gets more complex, the order of the system, so the higher, so the m and n here becomes larger, so it becomes harder to analyze. So what is our objective? Our objective via the Laplace transform is basically to transform this differential equation into an algebraic equation. So namely, what we want is to transform these derivatives here, okay, into additions and multiplications. So we don't want anymore to have time derivatives in our relation between the input and the output. And one way to perform this transformation is through what is called the Laplace transform. So what is the basic idea behind the Laplace transform? So the Laplace transform, essentially, it is a map, okay, so a function that takes as an argument another function here, okay, so small f. This f is a signal that is defined for positive time, which is real valued. So the Laplace transform takes this function as an input, and it gives as an output another function that I call here big F, or the Laplace transform or small f, which is a complex value functions that maps a complex number s into the complex number f of s. And now this function verifies various important properties. Three of them are as follows. we have first what is called linearity. So if you take the Laplace transform of a1 plus f1 plus a2 plus f2, here f1 and f2 are functions and a1 and a2 are constants. So this gives you a1 times the Laplace transform of f1 plus a2 times the Laplace transform of f2. So this is first property, linearity. The second property is if you take the Laplace transform of the time derivative of f with respect to t, this gives you the complex number s times the Laplace transform of f minus f at time t equals 0. Okay, so this is a formula. The Laplace transform of df over dt is s times the Laplace transform of f minus f at t equal to 0. Now you can use this expression here, this formula, to get the Laplace transform of the second order derivative of f. So the Laplace transform of d2f over dt squared is the Laplace transform of the time derivative of the time derivative of f. Okay, so this will give you s times the Laplace transform of the time derivative of f minus the time derivative of f at t is equal to 0. Okay. Next, you apply the Laplace transform on df over dt. You do the algebra, and at the end, what you get is s squared times the Laplace transform of f minus these terms here that depend on what's called the initial conditions. Okay, so f and its time derivative at time t equal to 0. And now, by induction, you can continue like this, and you get the Laplace transform of the nth order derivative of f with respect to time. So you see here that this nth order derivative becomes s to the power n. So you transform here the differential operator into an algebraic term. So here, this polynomial term s to the power n, that multiplies then the Laplace transform of f plus a bunch of other terms that depend only on the initial condition at time t equal to 0. So this is the key property. Recall what I said before. The goal is to transform our differential equations into algebraic equations because algebraic equations are easier to manipulate. So as you can see here, this property of the Laplace transform will help us to transform the derivative terms into polynomial terms, to move from the differential operators into algebraic terms. Another property is that the Laplace transform of the integral of a function is 1 over s times the Laplace transform of f. This formula here will be important later on when we will study PID controllers. Now, okay, so I said we want to transform differential equations into algebraic equations, and for this we have a tool that is called the Laplace transform, and which verifies these three properties among other properties. Now, what is exactly the Laplace transform? So the Laplace transform is given by this formula. Okay, so recall it takes as an argument a function small f, and to compute the Laplace transform of f, you just integrate, okay, from 0 to plus infinity, this function f of t multiplied by exponential minus st, where s here is the argument of the Laplace transform of f. Okay, is a complex variable here. And of course, this Laplace transform is well defined as long as this term here, okay, the exponential minus st times f of t, is integrable. So basically that this integral here is finite. Okay. So now we will try to apply the Laplace transform to our previous example. So recall we had this electrical circuit with the input voltage U, the current I of t, the resistor, and the output voltage Y of t. So we saw at the beginning that the differential equation that is verified for this circuit is given by dy over dt plus 1 over rc times y of t plus 1 over rc times u of t. Now, what I will do is I will apply the Laplace transform at the left-hand side of the equation and at the right-hand side of the equation. So I get the Laplace transform of the left-hand side is equal to the Laplace transform of the right-hand side. Next, I will apply the first property of the Laplace transform, which is linearity. So the Laplace transform of this term here is the Laplace transform of the first term plus, so this is a constant, I take it out, so 1 over RC times the Laplace transform of y of t. Okay? And here, same thing, I take out 1 over RC, I get 1 over RC times the Laplace transform of my input. Okay, now some notation, I will call big U of S the Laplace transform of my input, and big Y of S the Laplace transform of my output. So what we get? So this equation here can be rewritten like this. So I just replaced the Laplace transform of Y by big Y, and the Laplace transform of U by big U. So this is my notation. Next, I will use, so here you see that you have the Laplace transform of the time derivative of Y. So what you will do here is you apply the formula for the Laplace transform of the derivative. So recall, what you do is that you get S times the Laplace transform of small y, which is big Y of S, minus small y at time t equal to 0. So this is the Laplace transform of dy over dt. Okay, plus you have the other terms here. Now I will take big Y of S as a factor. So we get S here plus 1 over RC. I take small y of 0 to the right hand side, and this is the expression that I get. And here, the key, you see that I don't have any more derivatives. Here, I just have algebraic equations. So I just have my signal here that are multiplied by some polynomials. Okay, so here polynomial of S. And here you have a constant, and here another constant. Okay, so you have your signals that are multiplied by some polynomials of S here, plus a bunch of constants, and these constants will depend on the initial conditions. Okay. Now I will divide both sides of this equation by S plus 1 over RC. I can do this whenever S is different from minus 1 over RC. Okay, so I get this. And here you can see that basically I get two parts in the expression of y of s. I get the first part that depends on my input, okay, and the second part that depends on the initial condition. Okay, so this term that multiplies my input is called the transfer function from my input to my output. So this is the link between my input big U and my output big Y. Okay, so you have this first term plus a term that depends on the initial condition. Okay, so plus the impact of the initial condition. And this is the idea. Okay, so we had a differential equation, we apply the Laplace transform, and then we get something that is algebraic in the variables big U and big Y. Okay, so you don't have any more derivatives of the signals of interest. So you don't have a dy over dt and du over dt. We don't have this. Okay, you just have constants, polynomials in S, and my signals u and y. Okay, so now we can go back to the general expression of linear system. So this is the general formula that we saw earlier, and we will try to apply the Laplace transform here. Okay, so if I apply the Laplace transform on the first term, what I get is s to the power n times y of s plus a bunch of terms that depend on the initial condition here. Okay, so all these things here, they depend only on s and on constants. These constants are the initial conditions. For example, y of 0, dy over dt at time t equal to 0, the n minus 1 order derivative of y at time t equal to 0, and so on. Okay. For the second term, I get a n minus 1 times s to the power n minus 1 times y of s, plus a bunch of terms here that depend on s and on the initial conditions, okay? And so on until, so this term here becomes, so the a1 dy over dt becomes a1 s big Y of s, and here plus the initial conditions, and here the last term becomes a0 times big Y of s, okay? So this is the left hand side. Now for the right hand side, what I get is bm times sm u of s. So I had here bm times the mth order derivative of u with respect to t. So this becomes bm s power m times big U of s. Okay, plus a bunch of terms that depends on the initial condition, and so on until b0 times U of s. Okay. If I do the algebra, I rearrange the terms. What I get at the end is so this polynomial here multiplying y of s. Okay, so this comes from here, s power n times y of s plus a n minus 1 s n minus 1 y of s, and so on until a0 y of s. So I take y of s as a factor here, common factor. I get s power n and so on until a0 times y of s. This is my term at the left hand side. This will be equal to another polynomial term times u of s. So this is bm s power m until b0. So this is this polynomial here, plus a bunch of terms that will depend only on s and on the initial conditions. So these terms here will depend only on s, the complex variable s, and other constants that are the initial conditions. So the output and the input and their time derivatives at time t equal to 0. Okay, so this is an algebraic equation. So the signals that are varying in the equation, so y of s and u of s, they appear like this. You don't have derivatives here. So you have just polynomials and the signals of interest, okay, plus other constants that appear here. Now, what can we say? So we can see here that if you get a linear system, okay, with an input u and an output y, you can obtain the output y just by multiplying your inputs by this polynomial divided by that one, okay? So basically by this fraction here that we call the transfer function of the system. And once you get this term here, you just add the impact of the initial conditions, okay? So you just need to do this. So you can study your system as if all the initial conditions are 0, okay? So you do all your analysis as if the initial conditions are 0. You get y is equal to the transfer function, so this over this times u of s. Once you do this, you add the initial conditions, and then you get your exact output signal, okay, in the Laplace domain. Laplace domain means y of s, okay, so after you did the Laplace transform. Now, furthermore, the key properties that we will see in this class, such as stability and so on, as we will see, they do not depend on the initial conditions, okay? So it doesn't matter the value of the initial conditions. That's why in all our analysis, we will suppose that all the initial conditions are 0. Why that? Because if you study stability, so something that we will define later on, the initial condition doesn't matter because you are dealing with linear systems. And if you want to get the exact expression of the output, you just do all your analysis, you get the transfer function, and then at the end, you add the initial conditions, okay? So it really doesn't matter, that's why we will suppose that initial conditions are always 0, okay? So if you suppose initial conditions are always 0, you get your output over your inputs is given by this fraction here, which we call the transfer function. At the end, once we did all the analysis that we wanted in the frequency domain, also called the Laplace domain, we can go back to the time domain by something called the inverse Laplace transform.